Now, guys, at the moment, I'm going to quickly look at a simple application of differentiation. In this case, we're talking about getting. Remember what we said at the beginning. We said a derivative of a function at a point was giving us the gradient of the curve at that point. You remember that? Okay. So now, let's say we've got a parabola like this. This is a equation of a parabola. Let's say we've got a parabola which is more or less running like that, roughly. That's a rough sketch, isn't it? So then, if we choose a point, like somewhere there, and we want to know what is the slope of that point there, our previous discussion actually showed us that the slope of the curve there is equal to the slope of the tangent. You remember that? So then let's do that. Let's say we've got a line here, and then let's say we've got a tangent line which passes through that point. Now this line is believed to have a single point there touching the line. So to want to find the slope of that, we should calculate the derivative. But now, one question you could get in this situation is that someone will say, okay, there is a curve, find the tangent at the point, let's say this point is x equals to 2. So obviously, if this point is x is equal to 2 and that's the function, then which means here we've got 2 comma f of 2, which is our x in this case, isn't it? So then that point will be what? Is 2 squared, is 4 times 2 is 8, there is 6, is 14, 15, is it? So which means that line and the curve, they pass at the point 2 comma 15. Now if somebody asks us, what is the equation of the tangent line at that point? What can we do? We must first of all reflect on the fact that any equation of a line can be written this way. All together. But we know that this one is the derivative of the line, which is the gradient of the line, which is the gradient of the curve at that point, isn't it? Because the curve and the tangent line share the same gradient. But how to get that? We then differentiate dy dx. In this case, I'm talking about the curve. Altogether, that function derivative will be 4x plus 3. Now, if we now want the m, we will say m, which is the gradient of both the curve, the function parabola and the tangent line. That will be derivative dy dx evaluated at the point x equals to 2. Then we substitute the 2 for x, we get 8 plus 3, which is going to be equals to 11. Then now we can say that line, the red line, the equation must be looking more or less like this: 11x plus c. Altogether. Sorry, plus c, not plus x, plus c. Now plus c. So we've done almost half of what we're supposed to do. Then to get c, what do we need to do? We know that this line and the curve pass through that point. Then we can substitute that point in here and we expect it to satisfy this equation. So then what we do? We substitute y for 15 equals to 11 multiplied by 2 plus c. Since that point belongs to the line, this is true for this line. Then from there, now we can calculate c. So what can we say there? Therefore, c is equals to what? 15 minus 22. Altogether. Then what's the answer there? Come again? Minus 7. That doesn't sound true. Why? Oh, sorry. I'm thinking of the gradient. I thought I was thinking, I'm calculating c. So c, yes, 7 is less than 0. So I mean, this is a rough sketch, isn't it? So we expect there somewhere there to be minus 7. So now rewriting our equation of tangent to be 11 x plus c, which is minus 7. Then simplifying that, we can write that 11x minus 7 altogether. But now, that's not the only question we can ask there. This is the question of a tangent line. The other question we can ask, which is very closely related to this, is the question of a normal line. What is a normal line? A normal line, if you've got a tangent line like that, a normal line would be the line. Let's get another color here. Let's say green. Get a line. Would be the line which runs perpendicular to the tangent. Let's shift it there and take it as. Then we know that the angle there is what? 90 degrees. Then you must recall something you learned from school. Two lines which are perpendicular to each other. What relates them? The gradient of the two, what happens? The gradient is -1. No. If this is the normal line, I can call the gradient mn, and we've got the gradient mt. So what can you say about the two? Okay, that's exactly what I'm expecting. So mn multiplied by mt. Mt is tangent of the gradient of the tangent. Mn is the gradient of the normal line. That should give you -1. So from that, again, this normal line passes through the same point, isn't it? Then you can now find the equation of the normal line. I'm going to leave that one for you to do. Altogether, it's just making mn here subject to the formula. Then you get your gradient. Then you proceed similarly and you get your equation of a normal line. All together, guys. So that's one of the first applications of differentiation we're going to get. The other one, which we're going to discuss maybe later, but I'll just talk about it now. If you've got a point like that, a turning point, a turning point like that one there, we know we can have a tangent to that. But how do you expect that tangent to be? How do you expect the tangent to be? Horizontal, oblique, what is it? What do you think? That tangent there, the turning point of the parabola, the tangent just runs like the tangent to the parabola. How do you expect that line to be? Is it oblique or is horizontal or is what? Horizontal. And then a horizontal line, what is the gradient? What is the slope of a horizontal line? 0, isn't it? So that tells you the fact that whenever you have got a function which has got a turning point somewhere, at that turning point, we must expect the derivative of that function to be equal to 0. Then we're going to use that again in some further applications. Then, but for now, I think let's stop there and say that's short introduction to applications to differentiation. Okay, thank you for listening.